Hi everyone, my name is Dmitry Yusupov. I work for NVIDIA, and today we're going to be talking about OVSDB Query Optimizer and some other work that we've done at NVIDIA while working on OVS. What do we mean by the need for scalability, and can we really make SDN control plane truly scalable and elastically enough so that we can support modern Kubernetes? For instance, versions 1.19 supports up to 5,000 nodes in production. Large topologies, we're talking about potentially thousands of endpoints, load balancers, namespaces, policies, which in fact will be producing pretty large over north and southbound databases. What about scaling beyond 5,000? What can we get to 10,000 at some later point? The question I'm trying to bring up here is what can we do meanwhile in potentially long term to build truly elastic SDN topology? One obvious thing that we looked at is oven resourcing. We figured that the different SKUs where for central we will use more high performance servers, and for HVs we typically either reducing memory by using some CPU caps or potentially even running on ARM devices can help. The central components such as NorthD, RAFT, OVSDB, CNI master, they can run on truly fast Intel CPUs, for instance, or AMD CPUs, while HV controllers, they can be either limited to like single core or maybe a small amount of memory, and that can help us theoretically get these deployments deployable even at a very large scale, but to some certain degree at DPUs and high latency edge IT networks. But today I wanted to have a deeper look at OVSDB and can analyze what currently we have so far as OVSDB design is concerned, and what's the thoughts here. Well, first of all, it was originally designed with the emphasis on read IO scalability, first and foremost, for the important reason because as long as we can very efficiently do read operation at scale, we can propagate the flow as a polling model all throughout the HVs. As such, we created so-called dynamic distributed caches, and obviously the side effect of this is stale read. So this is all good so far. How we still need to deal with stale reads here and there. The second thing that we added is we now have high availability with a simplistic RAFT-based cluster functionality built in, which is great. It definitely gave us more reliable SDN. However, as a result, no read after write guarantee, and writes become somewhat slow. In general, OVSDB is in memory very unique relational database with a certain consistency constraints and guarantees, which can only do optimized queries when UUID is used, and in all other situations it will fall back to the linear scan. So by looking at the implementation of what we have today and kind of trying to evolve UUID-based optimizer, we were thinking about introducing primary and alternate key indexes. At the same time, the idea was, okay, so if it's going to be new indexes, then we don't want new data structures to appearing in the code base, but at the same time, we want to reuse existing data structure. And luckily enough, HMAP data structures, they have fairly low overhead per additional index key. So we're talking about just 16 bytes. That's all per additional index key to be taken from the memory. Results optionally can be ordered. This is something we can do, for instance, if we use some additional data structure, but that would require, obviously, just for alternate key, some certain rework and modification to the schemas. So let's look at the primary key design as far as the schema is concerned. So the good thing is, in our modification with the primary key, with introduction primary key, we don't need any OVSDB schema change. So here you see the index name, which is corresponds to the column name, is essentially already propagated through existing address set table. And as a result, all we do is just look at this array and building additional HMAP index. So the good thing is, completely transparently, if we have this already marked in OVSDB schema, we automatically will get some performance benefits by introducing this primary key indexer. The alternate key design is unfortunately cannot be done without introducing new changes to the OVSDB. And the proposal here is to introduce new Boolean flag, alternate key, and if it is defined, then additional flag ordered, which will determine the direction of the order if specified. If not specified, it still can be HMAP. If specified, it's likely needs to be a B3 implementation. Okay, so we've done so far the primary key implementation, and we wanted to kind of measure the benefit of avoidance of linear scan. So here you see that with a fairly small table size of 4,000 rows, it's a single OVSDB instance with and without optimizer. We already have close to 3x improvement. With the larger tables, we actually see much more significant impact, and this is obviously microseconds, but the realization here is that, hey, this is, we're now talking about like 10 milliseconds just to traverse a table, just for one query, right? So the good news is, the larger table, the more impactful this change can be. Okay, one question which arrived recently is like, okay, so what are the benefits of enabling Query Optimizer in Oven? In case of primary key, we actually do have some cases, particularly on northbound database, and it likely will benefit any sort of updates and selects performance out of the box. For southbound database, not so much, unless the custom monitors and custom applications are used, still can be beneficial. So for alternate key, however, it can only benefit for the complex select queries, and obviously anywhere where user would execute non-UUID-based and non-primary key queries. Now, whether those queries exist today, as of right now, I'm not aware of, but it doesn't mean that we may not need to introduce such queries if we have the optimizer support for it, right? So if it's fast, then it's fast, then why not? And so on this slide, I wanted to kind of demonstrate that, hey, linear scans avoided, right? And but how much we actually see the benefit? Well, it's quite a bit, even though in this is very small database, by the way. Even though the numbers is kind of significantly lower than UUID requests, UUID-based queries, but we still see it's significant number, right? And UUID queries, so as we in the previous slides, as we saw, whatever the immediate kind of lookup we're talking about, depends on the CPU, roughly maybe like 50 to 100 microsecond per query. Now, for the linear, for the large tables, we're talking about potentially tens of milliseconds. So if you're going to be doing a mass here, you can actually, depending on what the table size and so forth, this query underscore primary counter actually demonstrates that the semis can be very significant. Doesn't be looked, okay, so it's kind of be looked at the things in perspective of what else can we do in the future and applicability of this query optimizer. What can we do? If we compare today, so today OVSDB is obviously a relational database with cross-table correlations and so forth, and nice monitoring API. The one idea came up, why don't we look at the key value interface because of its simplicity and potential scalability. Because of that, so we thought, why not? So we tried and we kind of added the key value abstraction on top of libOVSDB, which is a Golang library. And so the library is open source as OVSKV library. And the good thing is, now we can layer this library on top of VSDB, and theoretically we can do things like what ETCD hierarchical queries can do as well, like /a/b/c, and then we retrieve the entire hierarchy under C, which kind of gives you this power of key value interface. At the same time, we also added support for interpolation of the Go structures. So if you have like Go structures, you can save this structure into the OVSDB and load it back, and you can do the partial load or partial save. So this library is available, but also since we have this library, and one idea why we developed this library is to essentially to do some comparison with ETCD, and this is what we've done. So we've been actually quite impressed with the performance of OVSDB versus ETCD for a reason, of course. The number one reason is, of course, is because ETCD is not in memory, while OVSDB is in memory database. So all the GET requests, they pretty much are processed without entering any caches or searches or anything like that, so directly from the data set. If you do not do primary key optimization, the OVSDB is going to be significantly slower than ETCD. With primary key, in this case, it's significantly faster. So as we see, I'm disregarding the put and delete results as of now, but the get result is actually twice faster, right? Even more, which is quite impressive. The put and delete is because, and this is just single ETCD versus single OVSDB instance test, the put and delete difference is primarily attributed to the fact that ETCD always does networking operations even if it's a single node, whereas OVSDB does this only when it's connected as a cluster. So again, the benefit here is the design of OVSDB is more accurate and proper this way. But if you compare with 3-node RAFT cluster, OVSDB is still faster even on the put and delete operations. It's actually faster than ETCD, which is, again, write operations and optimizations that we've done over the years, and this is the result of it. But in case of RAFT, on a read pass, we actually 3 times faster, or even more, even less, close to 4. So which is kind of very encouraging, which means what we have is probably fits really nicely in the use case, and definitely there is interest to capitalize on what we have and make it potentially scale even better. So what's next? Alternatively to what we have today, we can figure out whether we need additional implementation of B3 or not for ordered queries. Also, if you look at the perspective of the recent DDLog work, we can actually, once we have that throughout, we can scale computation with D3log, right? So that means the computation not necessarily will be bound to just one CPU, but can actually be executed in parallel on many CPUs and many servers even. So with that in mind, we might need to think about, okay, why not to introduce multi-writer design and potentially see what we can do by leveraging existing RAFT and building something more scalable over the time. But also, why not to try to kind of see if we can use key value interfaces throughout, and not necessarily everywhere, but just for the certain scenarios where we in particular we need better scalability, better accessibility, so to speak. So maybe just for some tables we can enable key value interface. So this is my current thoughts as of right now, and these are the links and with references to the work that we've done so far. This is me for this talk, and if you have questions, we probably will have some sort of a forum, so you can ask the questions, and I'll try to answer if possible. Thank you so much for watching. Bye bye.